Hello and welcome to the screencast on the domain of rational functions. Because a rational function can be written in the form r of x equals p of x divided by q of x for some polynomials p and q, we have to be concerned about the possibility that a rational function's denominator is 0. Since polynomial functions have their domain as the set of all real numbers, it follows that any rational function is only undefined at points where its denominator is 0. Officially, let p and q be polynomial functions so that r of x equals p of x divided by q of x is a rational function. The domain of r is the set of all real numbers except those for which q of x, the denominator, equals 0. Let's look at some examples. Go ahead and actually pause the video and try to determine the domain of the following rational functions by locating where the denominator equals 0. Okay, so for r of x, we know that by the zero product property, if the denominator 5 times x plus 8 times x minus 4 is going to equal 0, then one of those factors would have to equal 0. So we have x equals negative 8 or x equals 4, which means the domain for function r is all real numbers except x equals negative 8 and 4. Next we have q of x with a denominator of x squared plus 25. Now you could do some reasoning right here and notice x squared is always positive or 0, and then if you add 5, you're never going to get 0 as an answer. So there's no real solution to this equation. Or you could start to solve it, and then again, okay, x squared, because that's squared, we're not going to have a negative as our answer. So there's no restrictions in this domain. We could let x equal anything, and the denominator will never equal 0. So the domain for q of x is all real numbers, again, because x squared plus 5 never equals 0. Lastly, for p of x, we look at our denominator, 3x cubed plus 9x squared minus 84x. We know the domain will be all real numbers except those that make the denominator equal 0. So we're going to factor to try to find those values of x that would make the denominator equal to 0. And we get 3x times x squared plus 3x minus 28, and we can factor that further. 3x times x plus 7 times x minus 4. So by the zero product property, we know that either x equals 0, x plus 7 equals 0, or x minus 4 equals 0. So we get x equals 0, x equals negative 7, x equals 4. So that these values make the denominator 0, which means the domain for p of x is going to be all real numbers except x equals 0, x equals negative 7, and x equals 4. So let's see what this looks like on the graphs of these three rational functions. So again, we said for r of x, the domain was all real numbers except negative 8, and we see this hole at negative 8. Now your graphing technology would actually miss that, so we'll talk about how to identify that hole in a future section. And then we also said x equals negative 4 was not the domain, and we see a vertical asymptote at x equals 4. For q of x, we said the domain was all real numbers, and if we look at this graph of q of x, there are no holes, there's no vertical asymptotes. The graph looks like it is in fact defined for all real numbers. And then finally, p of x, we said the domain was all real numbers except 0. So there's a hole there that, again, technology would miss, and we'll talk about in a future section. We said x could not equal negative 7, and there appears to be a vertical asymptote there, and x cannot equal 4. And we see another vertical asymptote there as well.